Hello team, today we are going to look at graphing polynomials. In particular, we're going to graph cubics and quartics. Any of the skills though we take from today are going to translate into even graphing polynomials of a higher degree though. So we're going to look at four, different types of graphs. Within that we have cubics and quartics. And then within each of those, in cubics, we're going to look at point of inflection form and a more general case. And then with quartics, we're going to look at a turning point form and then again a more general case. A lot of the themes you see in this, you've already seen in quadratics, and a lot of it applies. We're going to step by step it through with the cubics to get a bit of a feel for it, but with the quartics will be a bit quicker because we should be fairly familiar with it all. So let's jump straight in. Let's start with the graph of a to the x cubed. So we're looking at this one. It's pretty straightforward. I'll come down over here though. It goes up and has that sort of shape. Actually, let's undo that. The general shape is that, a bit of a wave, and we have this what we call point of inflection here, where we go from the gradient decreasing to the gradient increasing. It inflects, and that's why it's called a point of inflection. We can see in this graph up here that if we have a negative in front, this actually reverses and it comes down, point of inflex, and goes onwards like that. If we have a positive, it is up like so, point and flex, and keeps going. And then if we put a coefficient, which the green line is showing, okay, if we have a fractional less than 1, we get a bit of a dilation going on and stretching it. You could either think of it as dilating horizontally along the x-axis, or you could also consider that you can get a similar shape by dilating vertically. But A either leaves it regular, so starts down bottom left quadrant going up, or if A is negative, then it starts positive values of y going down to negative values of y. From there, we can start to apply some more transformations. We can apply a plus k on the end, which acts as a vertical translation. A positive value of k, positive values of k result in a vertically up, or translating along the y-axis upwards, positive direction of the y-axis. And if k is negative, well, then it is translated down. We can also put a minus h within the cube. In essence, we're taking away h directly from x before any other operators are done to it, and in that case it creates a horizontal translation. In this case, we have to be careful with what notation we use. We need to note that there's a negative sign here in front of the h. So if h itself is positive, it's going to appear like you can see in this one, which is x minus 2 all cubed. Even though it's minus 2, the h value itself is positive, because in this form the sort of negative is in front. We result going to the right, and then the flip case there, which is x plus 5 all cubed, results in a translation to the left. So some people like to try and read the whole number there as h. Others consider it by itself, and then there's actually the standard notation is to put the negative in front of it. Either one works as long as you recognize that when the whole thing appears negative, you go to the right. When the whole thing appears positive, it's translated to the left, which results in what we call the point of inflection form. This, if we combine all three of those transformations, we get what we can use as, that's a terrible axis, but what we can use as a pretty easy thing to graph. Just like turning point form of a quadratic, we can end up with some cubic where that point of inflection is actually going to occur at h comma k, and then the A impacts dilation or reflection. We're flipping it up and down. But that's what we call point of inflection form of a cubic. As soon as you can see it written like that, where it's as a cube with a h or k, and sometimes those values won't appear, but it is a point of inflection form cubic. So for example, if we have a quick question where we need to graph a cubic that might be f of x is equal to x minus 3 all cubed plus 2, we can recognize that in this case h is 3 and k is 2. Therefore, let's say that's a 3, that's a 2. Our point of inflection will occur at that point. And our graph, our function will look something like that. Now, I haven't actually calculated what the intercepts are, which you would normally do, but that's a skill we know how to do from linear and quadratic, so I'm not going to go over it. Just let x equal 0, let y equal 0. But the key skill here is recognizing what's our h, what's our k value. That gives us our point of inflection, in this case 3, 2, which is a key point on that graph. So that is cubic point of inflection form. Let's look at the more general case of cubics, because not all cubics can be represented like that. Actually, they're nowhere near as common as the more standard type of cubic, which is shown here, which doesn't have a point of inflection, but it actually has 2 turning points. The key first thing we need to recognize about a more general form is, again, what is that A value? If A is positive, as shown here, okay, the net result is, as we go to the right, our graph is going to go up on average over the whole course of the function. So up, down, but then back up. So you start bottom left and you're ending bottom right. On the flip side, if A is less than 0, so A is negative, and A is always the coefficient of the x cubed term, but if A is less than 0, then as a whole we're going to head down as we go to the right. So we start high, go low, back up a bit, and then back off. So very much similar to positive and negative gradients of linear graphs. The overall trend of the cubic, if A is positive, start low, end high. If A is negative, start high, end low. From these general forms, you can sometimes factorize, or factorize to some extent. Now, how many factors you get depend on how many intersects the functions have. In both cases that I've drawn, both of these graphs have 3 intersections. That would mean you'd be able to factorize it into this form here, which we call intercept form. It's showing us where our 3 intercepts are, which happen to be B, C, and D. And which order they occur in is just the size and values of the numbers. It might be in this case that's B, that's D, and that's C. But if you get 3 factors, means you have to have 3 intercepts. There's something that we need to be careful of, and this holds true in quadratics, holds true in cubics, it's going to hold true in quartics and every polynomial, is what happens if you have a repeated factor or intercept. For example, if we have, like in this picture here, that is 3x plus 1, but that's squared, it's a repeated factor. So this function could have been written as 3x plus 1 bracket x plus 1 bracket x plus 5. Okay, but that x plus 1, since it's repeated, we can write it as square. If you ever have a repeated factor, that intersect is actually going to be where the turning point is. That repeated, as soon as that intercept is repeated, that then becomes a turning point. And that's true of quadratics, that is true of cubics and quartics, that if you can factorize and has a repeated factor, or what we call a repeated root, then the intersection is a turning point. And that really helps you build an idea of the shape of a graph. So if we do a quick example, let's graph 3x plus 2. Let's do 2 examples, x plus 1, x minus 1. If we're in an intercept form, we can see that our intercepts are going to be x equals -2, x equals -1, and x equals 1. There are intercepts. So we can straight away plot them. So we get -2 there, -1 there, and 1 there. And after we have that, all we need to realize is go back and look at the A term and go, where do I need to start? Do I need to start bottom left, or do I need to start top left? In our case, since we've got a positive, I need to start here. Now, the only place that this cubic can go is up through the first intercept, and then from there, it has to go back down through the next, keep going down, but then has to go back through the third one and then out. Okay, so the key here is identify your intercepts, put those dots down, and then look at your A value and go, where do I need to start? Top left, bottom left, and then you can work through. Let's erase. Oh, my brush size went massive. Let's erase that quickly, and we can do another example, maybe with a repeated root. Okay. Here we go. Let's do -2x minus 2 all squared x plus 1. Okay, so from that we want to identify our intercepts, so we know that x equals 2 is an intercept and x minus 1 is an intercept. So let's put those down. So -1, and then we also have 2. From there, go back, look at our A value. So in this case, it's negative. So that means we need to start high and low. So we have to start up here. So what happens? We have to come down, and now our -1 intercept is not repeated. So that's going to be a going through intercept. We're going to keep coming down, and then we need to come back towards our intercept. This intercept, though, is a repeated one. So since it's repeated, we're just going to touch, we're just going to kiss the axis, and then head back down and away. So to summarize, if the factor is linear in that it's a single one and it's not repeated, then that intercept is going to cross through. If it is a repeated factor, then it is going to have a turning point at that intercept. And that's cubics, graphing cubics. The skill of getting to that factorized form is everything else we've done prior. You can use factor theorem, you can use remainder theorem, you can use long division, synthetic division, equating coefficients, whatever you want. But that's why it's important to be able to factorize this, so you can then graph using the intercepts. Right, on to quartics. This is the turning point form, and like I said, we're going to go through this a little bit quicker. The same principles apply as up here in cubics or quadratics. You have a h, you have a k value, you have an a value in turning point form. So here and there, that is turning point form of a quartic. Quartic because it's to the power of 4. The same principles apply as turning point, that if A is greater than 0, it is a U shape, and if A is less than 0, well then it's an inverted U shape or an N shape. From there, H tells us X coordinate of the turning point, and K tells us the Y coordinate of the turning point. The thing to notice, and you might notice looking at this picture, it's not just poor pixels, is a quartic has a much flatter bottom than a quadratic. This is, you need to think about what is happening to, say, like small x values, especially around here if we're looking at a non-translated one. What happens when you put a small decimal to the power of 4. Well, a small decimal times by a small decimal gets smaller. Like 0.4 times by 0.4 actually becomes 0.16. They get smaller in size. If you then times that by 0.4 again, it gets smaller again, and then times by 0.4 it gets smaller again. So those values all the way up until just really close to 1, they get compressed, making them to the power of 4. So even, for example, 0.8 to the power of 4 is actually, let's go decimal, is less than a half. It's only really close to 0.4. So that's why, and if you're ever having to draw a quartic, you want to really make sure, or a turning point form of a quartic, you really want to make sure that that bottom side of it up until x is less than or greater than 1 away from the turning point is really compressed. As soon as you get past that 1 away, once you're into like even, where's my pen, 1.1 to the power of 4, even that starts to grow really quickly. We're almost at 1.5. So it's a real sudden change, that distance that is plus or minus 1 from wherever the turning point actually happens to be. Again, A itself also, the value of A acts as a dilation factor. But that's the turning point form. If you're asked to graph one of those, identify your H and K value, plot them. If it happens to have an intercept, then find those as well. Fairly straightforward. Let's jump into the general form. No, this is what it looks like, starting to get a lot meaner looking than a quadratic, but same idea. Have a quartic term, have a quadratic term, cubic term, linear term, and a constant on the end. If A is positive, okay, just like up here, it starts high and ends high. If A is negative, it starts low, ends low, but we end up with this wave in between. It's more of a W or an M shape. As you can start to see already in the picture on the right, though, those tips or turning points don't have to be at the same height, depending on what the equation is. Sometimes they will be at the same vertical coordinate, but a lot of the time they're actually offset, where they'll be at different heights. It's not a perfect W or perfect M. Sometimes you might have that, and same inverted. They're not always absolutely perfect. So that's our impact of A value, and then the rest of it follows the same trend as quadratics and cubics. If a factor is x minus e, if it's a single, let's call it a single intercept, then it crosses the axis. Okay, so we have a type of a factor, and then what happens at the axis, the x-axis. Well, if it's a single intercept, then it crosses. Same as quadratics and cubics. If we have a repeated, okay, then at that case, it is a turning point. We then, because we're in the form of quartics, we can actually go to a cubed factor. Now, what happens if it's a cubed factor? Well, let's think back to what a basic cube graph is. It's a point of inflection, and that's actually, okay, what happens at the intercept. It actually turns into a point of inflection. So we're starting to build a similar trend. This holds true for any type of polynomial. If it's a single factor, well then that intersection needs to be crossing the axis. If it's repeated, it's a turning point. If it's cubed, it's a point of inflection. If you happen to have to graph some polynomial that its highest order was to the power of 7, then you might have a quartic factor repeated 4 times, and then that intercept is going to look like a basic quartic. So you can use what the prior graph looks like, basic form of it, to figure out what that type of intercept will be. So let's do a couple quick examples. Let's graph, I'll write out the equations quickly. We'll do that one. We'll do x plus 3 to the 4 minus 7. And let's do x plus 3, x plus 2, x minus 2. Let's put a negative in front of that, and x minus 5. There we go. Okay. Let's start with the middle one. Okay, this is our turning point form of a quartic. So we can read off, in this case, our h value is -3 and our k value is -7. Now, I was saying before, like you could have an intercept or repeated factor to the power of 4 times, and you have a quartic at that intercept. This is not going to happen. Our quartic turning point is at this h and k value. And why is that the case? Well, because the -7 is outside at the end. We're not able to write it as just a bunch of factors multiplied together. We have this 7. Okay, so it's a turning point with a h and a k value. In this case, it is -3, -7. So I'll put that there. And then for a quartic turning point form, I like to make it really clear that it's fairly flat at the bottom and then gets up really quickly. And of course, you would have to then try and find those intercepts if you're doing a full graphing question to get full marks. So there's a turning point form. Find your h and k values, bang that in, put a pretty flat bottom to it, and then go from there. Let's jump to the left-hand one, and we can quite quickly see we have that repeated root. So we have intercepts at x equals 4, x equals -2 repeated, and x equals 3. So let's mark those. We have -2, we have a 3, and we have a 4. Okay. From there, we need to look at our a value, or is this a positive quartic or a negative quartic? In this case, it's going to be positive because there's no negative term out the front. So that means we have to start high and we're going to end high. Now, how are we going to do that? Well, repeated. So that means we come down, we just kiss that intercept, back up, and at some stage, we're going to have to come down. This one's a single intercept, single factor, so we go through, and then we have to go back through and put our arrows on. Got our 3 intercepts. We just need to find our y-intercept, and we're good to go. Let's come over to our very last one, and then we'll be done for the video. We can see they're all 4 different factors, so nothing's repeated. So let's fill them in. We have something at -2, we have something at -3, we have something at 2, and we have something at 5. Now, since this is a negative quartic, means we have to start low and end low. So we're going to come up, go through, come back down through, back up, back down through. Now, at this stage, we don't know, and we don't have a way, unless we start substituting a heap of values, to sort of roughly figure out how high those turning points are. And same over here, don't know. We don't have a method yet to find out where they are. Once we do calculus and we look at derivatives, we will be able to do that. But for now, we just put something roughly in, and that's all that's needed. That's it for the video. To summarize, we've looked at cubics, 2 different types, and we've looked at quartics, 2 different types. all the skills we've learnt from quadratics still apply. Find intercepts and graph. If you have any questions, let me know. Otherwise, have a good day.